Development and evolution, or ontogeny and phylogeny, respectively. Is there a relationship between the two? That's what we're going to be looking at in this segment. There's a term called heterochrony, which means a change in the timing of developmental events across evolution. In other words, there will be the appearance of certain traits at particular times of the life cycle in an ancestor that somehow have changed, not the traits themselves necessarily, but when they actually appear. And that's what we're talking about when we're dealing with heterochrony. It's something that was first discussed in a 1940 book by Sir Gavin de Beer called Embryos and Ancestors, which to this day is an excellent book if you can find it. It's now in its third edition that was published in 1956. But other books have appeared since this that have also really amplified our understanding of heterochrony, starting with Stephen Jay Gould's Ontogeny and Phylogeny. And here's yet an even more recent one that's called Heterochrony by McKinney and McNamara. And there are others as well. That's just a small sample. So you may never have heard this before, but you're hearing it now. So, heterochrony, there's two main types. Neoteny, a slowing down of development. Another way of thinking about that is a retention of juvenile characteristics into adulthood. Or we don't even have to specify the periods. We don't have to say juvenile versus adult, because it could be embryo to juvenile, for example. Just from a younger stage to an older stage, a slowing down in the timing of developmental events across evolution, from younger to older within any given descendant, relative to the ancestor. So that's one kind of heterochrony. And the other is the opposite. It's acceleration, a speeding up in the timing of developmental events in the descendants relative to when they developed in the ancestor. Now, I understand that might be difficult to follow, so let's look at it visually. So here we have some traits from younger to older. Okay, doesn't matter what the actual ages are. So the ancestor, I'm just going to call these traits A, B, C, D, E, F. Okay, so A, B, and C appeared in the younger stage of the ancestor. D, E, and F appeared in the older stage of the ancestor. So that's our frame of reference. So let's look at neoteny. Notice what's going on here. We have A, B, and C, which appeared in the young ancestor, but don't appear until the older descendant, a slowing down of development. It took longer for those traits, whatever they were, to actually develop. Neoteny. Acceleration, well, DEF was in the older stage of the ancestor, but now these traits are appearing at a younger age in the descendant. They've been sped up in time. Okay, so that's what heterochrony is all about. And now we'll look at some examples. Starting with acceleration. We have more examples of neoteny than there are acceleration, but I have a few classic ones here for acceleration. Precocial development. Okay, notice what's going on with precocial development. A speeding up of development. So there we have, just for example, we have some newborn mice over on the left. And over on the right, we have a newborn guinea pig. My gosh, its development has been sped up considerably relative to the mouse. Now, okay, let me just make sure you understand this. Guinea pigs did not evolve from mice. So that what I'm giving you is really not an evolutionary lineage right here. I'm just using these photos to illustrate how development can actually be accelerated in a very precocial animal relative to what would be called an altricial animal, such as the mice, where they are still quite helpless and underdeveloped in a manner of speaking at the time of birth. So a speeding up of development in the guinea pig. In humans, we have the amnion.
The amnion forms a fluid-filled sac that cushions the embryo.
Okay, so what's the developmental history of that across evolution? Well, in primitive mammals, the embryo develops first and then the amnion develops around it. But in humans, the amnion forms first and then the embryo develops after that. A speeding up in the timing of development of the amnion in humans. Now, of course, you could also argue, and you wouldn't be wrong for arguing this, that, well, okay, but couldn't you also say that the development of the embryo has actually been slowed down if it's occurring after the amnion? You could say that. That's why these two cases that I've just given you of acceleration is a tricky one relative to neoteny. I think the cases for neoteny are much more straightforward. So yes, there's a little bit of finessing, to put it nicely, when I'm giving you these particular examples of acceleration. This one less so, however. So this is an adult hyena. Notice those teeth. Notice the canines. Oh my gosh, you don't want to put your hand in the mouth of that animal. Well, there is a newborn hyena. The development of those canines has been sped up considerably because they're now appearing in a newborn. And you don't see those kinds of canines in the newborns of other canids, but you do in the hyena. And in fact, hyena pups engage in siblicide, so they will actively try to kill one another shortly after birth, and sometimes quite effectively, those canines give them the power to do that. Okay, let's move on to neoteny. So look at the shape of the newborn chimpanzee, or at least a young chimpanzee. It's not really newborn, but it's certainly a very young chimpanzee relative to the adult chimpanzee. Wow, the shape is very, very different. Well, what about human shapes? See, the shape of our head is more like the shape of the newborn chimpanzee than it is the adult chimpanzee. So we have retained this characteristic, this shape, into our adult stage. We don't go into that shape of the adult. Our spaces just don't elongate like that. The same with ape and human toes. So there's a fetal ape, there's an adult ape over on the left. And you can see that there's a narrowing of the toe in the adult relative to the fetal ape. Look at humans. There's a fetal human and there's an adult human, and we retain this characteristic of the younger form into our adult stage. Look at dogs and cats. Again, there's no evolutionary relationship between dogs and cats, but I just want to point out what happens to changes in the shape of the skull. So the infant dog and the adult dog on the top, notice the narrowing of the adult dog. The infant cat and the adult cat down below. So the shape of the skull of the adult cat is quite similar to the shape of the same species when it was an infant. Cat suckling and kneading. So when kittens do this, it actually stimulates milk production. So it's very important that newborn cats knead like that so that they can suckle. Well, what about adult cats? They're still kneading. They're not stimulating milk, they're just kneading. Actually can be pretty annoying if their claws haven't been snipped. But nevertheless, this is a behavior that's been retained into adulthood, neoteny. The evolution of flightlessness. Okay, so there are flightless birds. I mean, like ostriches, for example, the rhea from South America, and this extinct Hawaiian goose, the Thambatochen. I guess that's how it's pronounced, by the way. I'm not 100% sure. Doesn't matter, it's extinct, but it was flightless. The adults were flightless, which for geese is kind of unusual. Let's look at the skeletal structure of the adult Thambatochen. Notice the two bones of interest here, the scapula and the coracoid. There's a wide angle, very wide angle, where they come together, okay? Now remember, this is flightless. This is an adult, and it's flightless. Here is a young flying goose, a modern goose that's capable in the adult stage of flying. But of course, the hatchlings can't fly. Well, let's look at those bones. See, the young hatchling of a flying goose also has a wide angle between the scapula and the coracoid. But the difference here is when this goose grows up and becomes an adult goose and is now capable of flying, that angle sharpens up. So there's a change in that angle that facilitates flying, and that never happened in the flightless Thambatocean. They've retained the wide angle into their adult stage. Neoteny. Orchestea, or sand fleas. Orchestea is the genus name. And there's 3 different varieties of Orchestea, different species. So we have the intertidal form. That's what you find on the ocean, on the beach. The tide goes out, and these guys come out from underneath the sand, and then the tide comes back in, and they go back underground, under sand, whatever. Then we have freshwater aquatic, and the most recently evolved form is actually terrestrial. And what's happened here is a very interesting form of neoteny, where the adult terrestrial form has retained juvenile characteristics of both the intertidal and the freshwater form. What are those juvenile characteristics? Well, smaller gnathopods, and fewer pleopods back here, and a translucent skin. So those 3 characteristics are characteristics in the juvenile stage of the intertidal and freshwater form that have been retained into the adult form of the most recently evolved form, the terrestrial form of Orchestea. Salamanders. Okay, there is an adult ambystoma that I've colored in blue. They're not really blue. And a larval ambystoma that I've colored in yellow. They're not really yellow. They do have colors, but I just made up these colors so that I could compare them with what I'm about to show you in black and white. But notice what's happened between the larval form, the young form of ambystoma, and the adult. First of all, these gills have disappeared. You don't see them in the adult. The flattened tail has become much narrower in the adult. Well, let's look at some other species of salamander. There's a whole bunch. Notice what's happened. In some, we have actually in all of them, we have the flattened tail over here, flattened tail over here, flattened tail down here, flattened tail down here. And then these 2 species here have actually retained the gills. These are all the black and white ones here are all adults. So they have retained the juvenile characteristics found in ambystoma into their adulthood. Retention of larval ambystoma features, flattened tail, and the gills. And here you can actually see there is a larval form of a species called the many-ribbed salamander, and you can see the gills very prominent. The flattened tail is outside the picture, though. But here is an adult streambed salamander, and you can still see it. It has retained these gills that are found in larval forms of other species of salamander. Finally, aggression in rats. So now we're going to be looking at a behavior. And here we have some rats that are fighting it out. Rats can be sometimes rather aggressive toward one another in certain circumstances. I mean, they're not always that way, but they're fighting. So this was a selection study. An experimenter wanted to select for a high-level line of rats. These are domestic rats, of course, and a low-aggressive line of rats. And so, he took the ones that were more aggressive and interbred them among themselves, and the ones that were less aggressive and interbred them among themselves. And on day 64 of age, he looked to see what he got. And sure enough, he developed those 2 lines. We have one that's engaging in many, many more aggressive bouts, the red ones, than the brown ones down below, the low aggressive line. Yeah, right. But look what happens if you carry it out to 180 days of age. You get a little bit more aggression in that high aggressive line. You can only be so aggressive after all. But look what happens to the otherwise low aggressive line. It's caught up. There's been a slowing down of the development of aggression in the low aggressive line. It just took them longer to reach that level of aggression age-wise, a slowing down of development. So you could think about that as a neotenic characteristic as well, even though in this case it's not a true evolutionary relationship. Okay, so development and evolution plus some non-evolutionary examples just to show you the differences between the two types of heterochrony, neoteny, and acceleration.